Yeah, very good afternoon, students.
Good afternoon, sir.
Yeah. So in the today's class, we'll take up the thermal properties of matter. Correct? No? Yeah. It's a very quite important chapter, students, as well as for board and for competitive exams. Thermal properties of matter. Yeah. In this chapter, we are going to deal about the study of the heat energy and how we are going to measure that heat energy. Yeah. What exactly this thermal properties of matter is going to deal? It deals about the study of the heat energy and how exactly it is going to be measured, the heat energy. Now, heat energy is no doubt it is one of the form of energy which is going to be transferred between two system or between the system and the surrounding. So heat energy is a form of energy which is going to be transferred, between two systems. It is going to be transferred between two systems, or it is going to be transferred from system to surrounding. System to surrounding. That form of energy we called as what? The heat energy. Now, when it is going to be a form of energy, can you tell me the SI unit of the heat energy? Since it is a form of energy, what will be the SI unit of energy then? SI unit of energy will be a joule. In the case of the heat energy, we are using the sign convention. We are using the sign convention for the heat energy. We are going to take positive or we are going to denote with negative. When you have to make it as a positive energy, heat energy, if it is gained by the body, if energy is gained by a body, if the heat energy is gained by the body, then the heat energy must be taken as positive. And if the body is going to lose the energy, if the energy is lost by the body, then we are going to consider the heat energy as what? The negative. Then if I say the energy is going to be transferred between the two system or a system to surrounding, it always flows from, heat energy flows from higher temperature to lower temperature. Heat energy always flows from which body to which body? The body which is at higher temperature. So heat energy always flows from higher temperature to lower temperature. higher temperature to lower temperature. Yes. Now, what is temperature then? What exactly that measures? Now you have to know what is temperature, what exactly it measures, and what are the different units we have for the temperature. Yes, students, actually temperature measures the hotness or the coldness of a body. Temperature is the one which measures the hotness or the coldness of a body. Temperature measures the hotness or the coldness of a body. What will be the SI unit for the temperature? Usually this SI unit for the temperature is going to be a Kelvin. With what unit we are going to measure the temperature? We are going to measure that in Kelvin. That is denoted with K. But also degree Celsius is mainly used in the temperature. And also we are going to use the Fahrenheit. So what are the other two units for the temperature? It is Fahrenheit scale or a degree Celsius. Kelvin, degree Celsius, and Fahrenheit scale. So these are the three scales we are using to measure the temperature. Students, here you have to remember how to convert from degree Celsius to Fahrenheit or degree Celsius to Kelvin. I hope you know how to convert the degree Celsius to Kelvin. To convert the degree Celsius into Kelvin, you know that the degree Celsius value plus 273, degree Celsius value plus 273 gives in Kelvin. So to get the Kelvin temperature for degree Celsius, if you take plus 273, that represents the Kelvin. Please remember this. Temperature in degree Celsius plus 273 gives the temperature in Kelvin. Similarly, if you want to find in the Fahrenheit scale, please remember the general formula. Fahrenheit scale temperature minus 32 divided by 180 equals to temperature in degree Celsius divided by 100. Or you can cancel with this 10 and 10. So TF value will be equal to 18 by 10. 18 by 10 is nothing but 9 by 5 temperature in degree Celsius. Then if I shift this minus 32 to the RHS, it becomes plus 32. So please remember the formula how to convert the temperature from degree Celsius to Fahrenheit. So temperature in Fahrenheit is 9 by 5 times of temperature in Celsius scale plus 32 degree. Yes. Can you convert? I'll take one example, students here. Can you convert minus 40 degrees Celsius to degree Fahrenheit? Can you convert minus 40 degrees Celsius is equal to what degree Fahrenheit? Will you do the calculation, students? Tell me the formula. Temperature in degree Fahrenheit is nothing but what? 9 by 5 times of the temperature in degree Celsius, that is minus 40 degrees Celsius, plus what? 32 degree. So degree Fahrenheit is equal to what is 9 by 5 into 40? 5 ones are 5 eights are. So 8 into 9 minus 72 plus 32 degree. What is minus 72 plus 32 degree? It is 40 degree, minus 40 degree Fahrenheit. Minus 40 degree Fahrenheit. Student, what is the conclusion here? Even the temperature in degree Celsius is minus 40. If I convert that into Fahrenheit, that is also going to be minus 40. So they may put an MCQ question here. What is the temperature at which the Celsius scale and the Fahrenheit scale are going to coincide, or going to be the same? So degree Celsius and the Fahrenheit scale are same for a temperature of minus 40 degree Celsius. So minus 40 degree Celsius and minus 40 degree Fahrenheit are one and the same. So this is how we are going to deal about the concept of the temperature. Okay. Now, in order to explain the concept, how the drawbacks have taken place in the case of the thermometers. So there are some drawbacks in the thermometers because of the expansion in the case of the liquids. Because when you give the heat energy to the liquid, it is going to expand. Because of that expansion, the thermometers may be not show a very accurate reading. So in order to avoid all these things, we are going to explain how this liquid or the gas molecules are going to behave. So in order to explain that, we have introduced some concepts of gas laws. One is called as the Boyle's law and the Charles law. So the first statement you must know, that is the Boyle's law. What is the statement of the Boyle's law? Students, in order to explain the concept of the behavior of the gas molecules, it has to be required the three very, very important parameters, that is pressure, volume, and the temperature. So these are the three physical important parameters we require in order to explain the concept of the behavior of the gas molecules. So which are the three important parameters? Pressure, volume, and the temperature. But we cannot study the analysis of pressure, the volume, and the temperature simultaneously. So one of the parameter is going to be kept constant. One of the parameter is kept constant, and we are going to deal how this variation is going to take place. So in the case of the Boyle's law, we are going to keep the temperature as a constant. So in Boyle's law, we are going to keep the temperature as constant. By keeping the temperature constant, we are going to explain how the pressure and the volume are going to vary. It is found that at constant temperature, the volume of the given mass of a gas is inversely proportional to the pressure. What is the Boyle's law statements? At constant temperature, volume of the gas molecule is inversely proportional to the pressure. Or you can say the pressure into the volume is a constant. Pressure into volume is going to be a constant. This is what we call as the Boyle's law equation. So what's the Boyle's law equation, student? Pressure into volume is constant. Then we are having another law, that is what we call as the Charles law. What's the statement of the Charles law here? In the case of the Charles law, we are going to keep the pressure as a constant. We are keeping the pressure as what? The constant. By keeping the pressure as a constant, we are going to explain how the volume and the temperature are related. It is found that volume is inversely, directly proportional to the temperature. Volume of the given mass of a gas is directly proportional to the temperature. So we can tell that the volume by temperature is going to be a constant. Volume into temperature is going to be a constant. This is what the Charles law equation. So this is called the Boyle's law, and the Charles law. Actually, one more law is there, that is Gay-Lussac's law, which is not there in our syllabus, students. In that Gay-Lussac's law, instead of keeping the pressure as constant, we are excuse me. In the case of a Gay-Lussac's law, we are keeping the volume as a constant and we are varying the pressure and the temperature. Pressure is directly proportional to the temperature. That is, pressure by temperature is a constant. Now, we are analyzing the gas which is going to obey both Boyle's law and Charles' law. We are going to consider that gas molecule is going to be obeys both the laws, which is considered as the gas laws. So gas laws are the one which obeys both Boyle's law and the Charles' law. So gas laws are the one which is going to obey both Boyle's law and the Charles' law. Obeys Boyle's law and the Charles' law. So if I combine that now, you can tell volume is directly proportional to temperature divided by P. V is proportional to T, Charles' law. V is inversely proportional to P, that is Boyle's law. If I combine that, I am getting V is directly proportional to T divided by P. Or I can say pressure into volume is directly proportional to the temperature, that is T. Then we are introducing one more constant here, that is R into T. R into T. What is that R represents here? R represents a universal gas constant. What is R represents? Universal gas constant. R is a constant called universal gas constant. Please remember the value of R, students. That is 8.314 joule per mole per Kelvin. What's the value of the universal gas constant? Universal gas constant is 8.314 joule per mole per Kelvin. This is what we consider as the universal gas constant. Now, I hope you got the concept of Boyle's law, students. Now, let me know what is the concept of the absolute temperature. What is the absolute temperature? Why we got the Kelvin scale? You can analyze that from here. What is absolute temperature? Student, if I plot the graph taking the volume versus the temperature, volume versus the temperature. In the case of this, by using the concept of the Charles' law, if I say volume is directly proportional to the temperature, as temperature increases, the volume also increases. But at 0 degrees Celsius, we couldn't get the volume as 0. If I decrease the temperature in the negative value, I found that the volume is going to be 0 at one particular temperature, that is minus 273.15 degrees Celsius. Actually, this temperature, we call it as an absolute temperature. So absolute temperature is the temperature at which the volume of the ideal gas is 0. So absolute temperature is the one, or you can say at which the volume of the gas, or also you can conclude pressure also. Volume or pressure of a ideal gas. Ideal gas. Ideal gas means which obeys that Boyle's law and the Charles law. That is, ideal gas is 0. At which temperature the volume of the gas becomes 0, that temperature we will call it as a absolute temperature. So they have designed, the scientist called by the name Lord Kelvin. Now Kelvin has designed the new scale temperature starting from 0 Kelvin. He treated this temperature minus 273.15 degree Celsius as 0 Kelvin now. So he designed one another scale now. This is measured in degree Celsius, right? Now he designed one temperature in Kelvin. Now in Kelvin, it starts from 0. Here, the value starts. So 0 Kelvin, 1 Kelvin, 2 Kelvin, 3 Kelvin, 4 Kelvin, 5 Kelvin, 6 Kelvin, 7 Kelvin, like that. So at which temperature the volume becomes 0 now? It is at 0 Kelvin. At 0 Kelvin, the volume becomes 0. So this will starting temperature now. This will be the starting temperature now. So this temperature is what we called as the Kelvin scale temperature. So what is Kelvin scale temperature? Kelvin scale temperature is the one which is designed starting from 0 Kelvin. At 0 Kelvin, the volume of the gas molecule comes to what? 0. That temperature scale was designed by the scientist called by the name Kelvin. So only that temperature we call it as the Kelvin scale temperature. I hope students, you got why the Kelvin scale temperature was introduced. Because with the degree Celsius temperature, we can't talk about the volume of the gas from 0 value. We will get a negative temperature. So only we have maintained the another scale that is called the Kelvin scale, which starts from 0. At that temperature, only the volume also starts 0. So only the new scale was designed. That scale only we call it as what? The Kelvin scale temperature. Kelvin scale temperature. Okay. Now, suppose what happens to the gas molecules if I supply the heat energy. For example, if I consider this is a system which is enclosing the gas molecules. For this gas molecules, or I can say the liquid. For this gas molecules or the liquid, if I supply the energy, if I supply the heat energy, what are the changes it is going to take place? If I if I supply the heat energy to this gas molecule, then there will be a effect on, What are the effect there will be now? There will be a effect on thermal expansion. So if you supply the heat energy to the gas molecule, there will be a thermal expansion. Thermal expansion means maybe the length or the area or the volume of the gas molecules may expand. Because of that heat energy, maybe there will be a rise in what? The temperature. There may be a rise in what? Temperature. And also there may be a change in the state itself. It may be changed to liquid to gas or liquid to solid or solid to gas. There will be a changes in the state. So students, what are the effects of the heat which is supplied to the gas or liquid molecule? There will be a thermal expansion or the rise in temperature or in the change in the state. Now, in detail, we'll talk about the thermal expansion. First, we'll talk about the thermal expansion of the solids. In the case of the thermal expansion, there will be an increase in the dimension. In the case of the thermal expansion, maybe there will be an increase in the dimension. Increase in dimension. So in the thermal expansion, maybe there is an increase in the dimension. Based on that dimension, we are classified into three types. One is called as the linear expansion. One is called as the linear expansion, that is denoted with the symbol alpha. Second one is going to be area expansion beta. Area expansion beta. The third one will be the volume expansion. The volume expansion gamma. So linear expansion, area expansion, and volume expansion. These are the three types of the thermal expansion. Now, let us go with the detailed explanation of one by one. That is linear expansion, thermal aerial expansion, and volume expansion. Now, here I'm going to consider a linear expansion concept. Then we can compare with area and the volume. Linear expansion. Now, I'm going to consider one rod, students, of length L. Let us say there is one rod. What's the length of the rod? Let it be L. L is the length of the rod. Now, for this rod, if I supply the temperature, in the form of heat energy, if I increase the temperature by delta T, what will happen? This rod is going to expand. This rod is going to expand. Let us say the expansion length is delta L. Expansion rod length is what? The delta L. Delta L is the change in the dimension of the rod. According to the concept, if you want to increase more and more change in the dimension, then you have to increase the original length or you have to increase that temperature. So increase in the length is directly proportional to the original length and temperature. To remove that proportionality constant here, we are introducing a constant called alpha here, that is L into delta T. This alpha is equal to the change in length, original length, into the change in the temperature. This alpha, we call it as the coefficient of linear expansion. What is this alpha called? Coefficient of linear expansion. Coefficient of linear expansion. So what is coefficient of linear expansion, students? It is nothing but the ratio of the change in length to the increase in temperature to its original length. That ratio, we call it as the coefficient of linear expansion. What will be the SI unit of the alpha? What is SI unit of alpha? SI unit of alpha is per Kelvin, because numerator length, denominator length will get cancelled out. So alpha is inversely proportional to the temperature. So SI unit will be per Kelvin. So that is the coefficient of linear expansion. Students, similarly, you can talk about the coefficient of areal expansion, that is change in area to the original area into the change in temperature. So this ratio, we call it as the coefficient of surfacial expansion, or you can say areal expansion. What is beta, students? It is coefficient of surfacial expansion. Surface means area. Surface expansion. Instead of talking about the area, if you talk about the volume, then it is called as gamma, that is coefficient of volume expansion, that is delta V by original volume into the change in the temperature. This is called the coefficient of cubical expansion. Cubical means 3-dimension. Cubical expansion. So gamma is the coefficient of cubical expansion. So there are 3 important expansion, students, that is alpha, beta, and the gamma. Now, there is a relation between the alpha, beta, and the gamma. Please remember, what is the relationship between alpha, beta, and gamma? Alpha, beta, gamma are alpha is to beta is to gamma is always in the ratio 1:2:3, because alpha talks about 1 dimension, beta talks about 2 dimension, gamma talks about the 3 dimension. So alpha is to beta is to gamma is in the ratio 1:2:3. That implies clearly beta will be 2 times of alpha, gamma will be equal to 3 times of alpha. So this is how exactly we are having the relationship between the coefficient of the linear expansion, surfacial expansion, and the cubical expansion. Now, you have to know the next concept, student, that is the thermal stress. What is that? Thermal stress. Let me know what is a thermal stress. What is the thermal stress? Suppose if I consider any metallic rod where the ends of the rod is rigidly fixed. Now, if I increase the temperature of the rod, the length is going to increase, but there will be no space left to increase its length. So it is going to start bends. The rod is not allowed to bend, then it will undergo a great stress. That is what we call as the thermal stress. For example, if I consider the rod, this ends of the rod is rigidly fixed. Both the rod's ends are rigidly fixed. Now, if I increase the temperature, actually the delta L has to increase, but there is no space to increase that, isn't it? There is no space to increase. Because when there is no space to increase, here there will develop a stress. That stress is what we call as the thermal stress. What is that called? That is called the thermal stress. Now, we can measure that thermal stress by measuring the Young's modulus concept. In the previous chapter, you have studied the concept of the Young's modulus, that is nothing but the stress divided by the strain. Stress divided by the strain. Here, what is the stress then? Stress is nothing but the Young's modulus into the strain. Young's modulus into the strain. Now, stress is equal to, you know what is the strain? Strain is the change in length to the original length. So, stress is equal to, this increase in length is because of the heat energy what you have supplied. So here you can say what is delta L by L, students. Delta L by L can be taken as alpha into delta T. Alpha into delta T. This is what we called as the thermal stress. So what's the formula for the thermal stress? Y into alpha into delta T. What is this Y called? Y is a constant called the Young's modulus of the material. So what's the formula for the Thermal stress. The thermal stress is nothing but the Young's modulus alpha into the change in temperature. Or also you can remember this formula Y into delta L by L. Delta L is the increase in length. Delta L is the original length. So this is the formula for the thermal stress. Students, please be very careful. They may be asked this question to explain the concept of the thermal stress. So in order to explain the thermal stress, what you have to put the concept here? You have to consider one metallic rod. Both the ends of the metallic rod should be rigidly fixed. For the fixed rigid rod, if you increase the temperature, what happens? If you increase the temperature, what happens? The rod will try to increase its length. But you can notice there is no space to increase its length. Because of that no space, it tries to bend, but the rod cannot bend. So there will be some thermal stress will be developed on the rod, that whatever the stress it has developed on the rod, that is what we called as the thermal stress. This is very important for 3 mark. Now, next question is also very, very important, students, which is frequently asked for the 3 marks. Now, they will ask us to show that coefficient of volume expansion that I will denote with alpha V. Instead of using gamma, they may be used alpha V. Alpha V tells the coefficient of volume expansion. You have to prove that this is equal to 1 divided by temperature. So show that coefficient of volume expansion is inversely proportional to the temperature. A very, very simple, students. They may be asked for the 3 mark. How to derive? Students, you know that the ideal gas equation is given by, we know that from ideal gas equation, we know that PV is equal to R into T, where P represents the pressure, V represents the volume, T represents the temperature, R is the universal gas constant. Now, here you have to talk about the volume expansion, isn't it? You're talking about the volume expansion. So now let us say the temperature is increased to delta T. This implies the volume also increases to delta V. Then what is the equation becomes? Pressure into, what is the change in volume? Delta V equals to R into change in temperature, that is delta T. P into delta V is equal to R into delta T. You can call this equation as 1 and this equation as 2. Now I can divide the equation 2 by 1. If I divide the equation 2 divided by 1, what is going to happen? You can notice that P into delta V divided by P into V will be equal to R into delta T divided by T. Now you can cancel with this pressure and pressure. Here you can take R, even your R and R will also get cancelled. So delta V by V, I will shift this delta T to the LHS, so it becomes 1 by T. Student, what is delta V divided by V into delta T? Look at this. It is a coefficient of cubical expansion. No, delta V by V into delta T. So it is a cubical expansion that is denoted with gamma, which is equal to 1 by T. But in the data, instead of using gamma, they are telling alpha V. So gamma can be replaced as alpha V, which is equal to 1 by T. So what is the formula for the coefficient of volume expansion? Coefficient of volume expansion is nothing but alpha V is equal to 1 by T. That is the reciprocal of the temperature. So this is another very important concept for 3 mark, which is very, very important, students. Frequently asked question. Addition to this, there may be a one concept question, student, here, that is, the anomalous behavior of the water. That is anomalous expansion of water. Anomalous expansion of water. What is that? Suppose if I take the concept, taking the density versus the temperature. You know that at 4 degrees Celsius, the density will be minimum. If I go on increasing the temperature, the density has to increase. But you can notice that from 0 degree to 4 degrees Celsius, from 0 degree to 4 degrees Celsius, instead of increasing the density, actually the density decreases, it reaches minimum, then after it start increasing. So from 0 degree to 4 degrees Celsius, the volume of the gas molecule actually decreases. You can take this as volume. Volume actually decreases. You know that volume is directly proportional to the temperature. As temperature increases, we should get the increase in volume, isn't it? But from 0 degrees Celsius to 4 degrees Celsius, volume start decreasing as the temperature increases. As the temperature increases, volume decreases from 0 degree to 4 degree. That abrupt behavior, that reverse behavior is what we call as the anomalous expansion of water. That is what we call as the anomalous expansion of what? The water. Here. So this is also one important concept. They may ask to explain the anomalous behavior of the water, or what is the concept of anomalous expansion of water. We have to tell from 0 degrees Celsius to 4 degrees Celsius, actually there will be a decrease in the volume instead of increasing. This reverse expansion or this reverse behavior is what we consider as the anomalous behavior or anomalous property of the water. Yes. Let us go to the next concept, student. That is the heat capacity and the specific heat capacity. Heat capacity and the specific heat capacity. Now, first, let me know the concept of heat capacity or specific heat capacity. Let us take specific heat capacity. Specific heat capacity. Yeah. In order to know the meaning of the specific heat capacity, students, let me consider one simple example. Let me consider one gas molecule or any substance. Let us say the mass of the substance is m. For this, I'm going to supply certain amount of energy. I'm going to supply certain amount of energy. Let us say you have supplied delta Q amount of energy to this substance. If I supply this amount of energy to this substance, what happens? There will be an increase in the temperature. I will take that increase in the temperature is delta T. From this, you can conclude if you increase more and more heat energy, if you give more and more heat energy, what happens to delta T? See here, if you take more and more mass, you require more amount of heat energy to increase the temperature. So delta Q is directly proportional to mass. And if you want to increase more and more temperature, then more amount of heat energy is required to increase more temperature. So delta Q is directly proportional to mass and the change in temperature. Now, to remove the proportionality constant, we are introducing a constant like S into M into delta T. This S is a constant called the specific heat capacity. So S is a constant here, that is nothing but the amount of heat energy required to increase the temperature by 1 degree Celsius in unit mass substance. So this S is called as the specific heat capacity. Specific heat capacity. So how do you define this specific heat capacity? Specific heat capacity is what? It is the amount of heat energy required. Amount of heat energy required to increase the temperature by 1 degree Celsius in unit mass substance. In unit mass substance, to increase the temperature by 1 degree Celsius, how much of heat energy you required? That amount of heat energy, we call it as what? The specific heat capacity. In this term, we are using the another thermal heat capacity, that is only delta Q by delta T. Delta Q by delta T is S into M. This is called as the heat capacity. Instead of unit mass, we can consider any quantity. For any quantity mass, if you increase the temperature by 1 degree Celsius, then that amount of heat energy which we required is considered as the thermal heat capacity. Now, instead of talking the mass in kg, if you talk it in mole, instead of talking the mass kg, instead of that kg, if you're talking in mole, then it is considered as molar specific heat capacity. Then we will call it as what? The molar specific heat capacity. Molar specific heat capacity. So SI unit will be the same, student, that is joule per kg per Kelvin. Then actually there will be two types of specific heat. Types of specific heat. Now you can supply the specific heat at constant pressure. At constant pressure, that is usually will denote with SP, or also you can denote that with Cp. So this S can also be represented with the C. So if the amount of heat energy is supplied at constant pressure, then it is called as the specific heat at constant pressure, that is denoted with the Cp. The second thing, if you supply the heat energy at constant volume, if you supply the heat energy at constant volume, then it is considered as the specific heat at volume, that is denoted by the letter SV or Cv. So what is Cp represents? Specific heat at constant pressure. And what is that Cv represents? Specific heat at constant volume. And also please remember, student, there is a relation between this Cp and Cv, that is called as Cp minus Cv is equal to R. This is called as the Mayer's equation. You can learn this derivation in the another chapter. This is called as the Mayer's equation or a Mayer's relation, that is Cp minus Cv is equal to R. Maybe you're going to learn this in thermodynamics chapter. So this is the concept related to the specific heat capacity. So what is specific heat capacity? It is the amount of heat energy required to increase the unit mass substance by what degree temperature? By 1 degree Celsius temperature. That is what we considered as the specific heat capacity. What are the different types of specific heat capacity? There will be two types of specific heat capacity. One is CP, the another one is CV. CP is the specific heat at constant pressure. CV is the specific heat at constant volume. All these units are going to be represented with joule per kg per Kelvin. So this is about the specific heat capacity. Now let us talk about the concept related to the change of state. This is also very important, student. Maybe they will ask for 1 mark. Change of state. It is for 1 mark MCQ questions. Now you know that there will be 3 states of matter, that is solids, then liquid, then gas. Now this is in the solid state. This is in the liquid state. This is in the gaseous state. Now you can convert from one state to another state. If you convert the state from solid to liquid, what is that called? Melting. At which temperature solid becomes liquid? That is called melting point. So what is melting? Melting is the change of state from solid to liquid. At which temperature the solid becomes liquid? That temperature we call it as what? What is that called? Melting point. Then, if you convert from liquid to solid, if you convert the state, if you change the state from the liquid to the solid, then it is considered as the fusion. Fusion is the change in state from liquid state to solid state. That is called as the fusion. This is also called the freezing. Freezing means liquid to solid. Liquid to solid is called the freezing. Okay. In this concept, they may put one concept here, that is regelation. R-E-G-E-L-A-T-I-O-N. Regelation. What is regelation? If you consider the ice, if you start melting that ice, when ice starts to melt, when pressure is increased, and again it freezes, freezes. If you melt the ice to a liquid state, if you start melting the ice to the liquid state, if you start increasing the pressure, it will start again freezing. It start again to freeze. This phenomenon is what we call as the regelation. So what is regelation? When pressure is increased, the ice starts getting freezed, and again the ice is going to get freezed. That phenomenon we call it as what? The regelation. In the case of the regelation, the pressure has to decrease here. So the pressure is going to increase, ice starts melting. It can freeze again back if you decrease the pressure. What is that phenomenon or that process is called? That process is called the regelation. So regelation is just freezing the ice by decreasing the pressure. That is what we called as the regelation. Then, what is the change in state from liquid to gas? The change in the state from liquid to gas is what we called as the vaporization. So what is vaporization? It is the change in state from liquid to gas. At which temperature that liquid becomes vapor? That temperature, you know, that is called as the boiling point. Then, here there is one more important term, student, that is solid is going to directly becomes the gas. The solid becomes directly to the gas. That is what we called as the sublimation. So what is sublimation? Sublimation is the change in state from solid to vapor state passing through the liquid state. That is what we called as the sublimation. You can consider the camphor. Camphor is in solid state actually. When you burn that, it is going to get into vapors directly. So that is what we called as the sublimation. Then, in this case, there is one more important point here. That point we usually will call it as a triple point. Triple point is the one. You know that there will be a three states, that is solid, liquid, and the gases. But at one particular temperature, solid, liquid, and gaseous, that is vapor, will coexist. That particular point we call it as a triple point. So triple point is the temperature. Triple point is the temperature at which solid plus liquids plus vapors all will coexist. All these are going to coexist. That particular point we call it as what? A triple point. That is what we call as the triple point. Now, during this changes, student, during this change of state, you require some amount of heat transfer. To change the state, how much of heat energy we require, that is what we usually call it as a latent heat. What is latent heat? Latent heat is the amount of heat energy required per unit mass to change the state. To change the state. To change the state per unit mass. In unit mass I'm talking. Per unit mass. To change the state per unit mass, how much of energy we require, that energy we call it as the latent heat. So energy per unit mass is called as the latent heat. Amount of heat energy required per unit mass to change the state. To change the state in unit mass, how much of heat energy you require, that is what we called as the latent heat. You may talk about the latent heat of fusion, or also you can talk about the latent heat of vaporization. So this is how the change of state is going to take place in the substance. If you have any doubt, you can ask students. Now, let us take the very important concept, that is calorimetry. What is that calorimetry tells? Actually, it deals about the measurement of heat. Actually, calorimetry is the device which deals about the study of what? The measurement, the measure of it. We can measure the amount of it by using the device called the calorimetry. So, in this calorimetry, we are using one principle. What is the principle of that calorimetry? Whatever the changes is taking place in the state, during that there will be a loss of heat energy from the hot body and there will be a heat gained by the cold body. These two must be equal according to the principle of calorimetry. So according to the principle of calorimetry, you have to tell heat lost by a hot body must be equal to the heat gained by the cold body. Heat lost is always equal to the heat gain according to the concept of what? The principle of calorimetry. Please remember that. According to the principle of calorimetry, amount of heat lost is equal to the amount of heat gain. That is the principle involved in the calorimetry. But we are going to use that principle of calorimetry in the case of the measurement. If you consider one simple example, there is a body A here. This body A is having mass M1, specific heat C1, temperature θ1. Now there is another body B here. This is mass M2, specific heat C2, temperature is θ2. Then if I mix this A and B, now there will be some intermediate temperature, isn't it? What is that intermediate temperature? Theta. Theta will be the intermediate temperature. If you assume θ1 is more than θ2, θ1 is more than θ2, what happens? Energy will flow from body A to body B, isn't it? Heat energy will flow from body A to body B. So this clearly tells that amount of heat energy lost from body 1, that is body A, M1 C1 C1, θ1 minus θ, where θ is the intermediate temperature. This should be the amount of heat gain, M2 C2, change in temperature, that is θ minus θ2. So if you simplify this for θ, you may get another expression which is going to be used only for your CT exam. That is M1 C1 θ1 plus M2 C2 θ2 whole thing divided by M1 C1 plus M2 C2. This is how we are using the common temperature of the substance. When the two liquids or gaseous are going to mix, what is the intermediate temperature it is going to attain? What is the common temperature it is going to attain? That common temperature can be calculated by using that M1 C1 θ1 plus M2 C2 θ2 divided by M1 C1 plus M2 C2. So this is by using the concept of the principle of calorimetry. Now, actually, we can transfer this heat energy in the three different forms. There are methods to transfer the heat energy. Methods to transfer heat energy. To transfer this heat energy, we have three different methods, students. The first method is by conduction method. By conduction method, you can transfer the heat energy. Second one, by convection method. The third one is about the radiation. So these are the three modes of heat transfer. So mention the three modes of heat transfer. The three modes of heat transfer is conduction, convection, and the radiation. In the case of the conduction, how the heat energy is going to be transferred? In the case of the conduction, how the heat energy is going to be transferred? In the case of the conduction, we are going to transfer the heat between the two parts of the body whenever there is a temperature difference is there. And in the conduction method, the heat energy is going to be transferred without the actual movement of the particles. So in the conduction method, we transfer heat energy. We transfer heat energy. We transfer heat energy without the actual movement of particles. Without actual movement of the particles, we are going to transfer the heat energy. That is what we called as the conduction. Now, according to the law of thermal conductivity, according to the law of thermal conductivity, whatever the amount of heat energy you have supplied is directly proportional to the area of that body, and it is directly proportional to the temperature difference, and it is inversely proportional to the thickness of the slab, and directly proportional to the time taken to transfer the heat energy from one end to another end. According to the law of thermal conductivity, amount of heat energy transferred in the body is directly proportional to area of the slab, directly proportional to the temperature difference of the rod, directly proportional to the time, and inversely proportional to the thickness of the slab. That is, Q is proportional to A T1 minus T2 into T divided by D. So Q is equal to some constant K here, K into A into T1 minus T2 into T divided by D. That K is a constant here. That constant K is called as the coefficient of thermal conductivity. What is that K constant called? Coefficient of thermal conductivity. And this is going to be measured with the unit watt per meter per Kelvin. Watt per meter per Kelvin is the SI unit of the thermal conductivity. How do you define this thermal conductivity? If I assume area is 1 meter squared, change in difference in temperature is 1 Kelvin, the time taken is 1 second, and the thickness is 1 meter. This clearly tells K is equal to Q. So how do you define that coefficient of thermal conductivity, student? Coefficient of thermal conductivity is defined as what? Thermal coefficient, thermal conductivity, coefficient of thermal conductivity K is equal to the amount of heat energy transferred across a unit area in a time of 1 second with a temperature difference of 1 Kelvin and the thickness of the slab is 1 meter. So amount of heat energy required to increase the temperature by 1 Kelvin in unit area, unit thickness in 1 second is called as the coefficient of thermal conductivity. Now, which is the second method we have in order to in order to transfer the heat energy? That is the convection method. So, second method to transfer the heat energy is convection. In the case of the convection, we are going to transfer the heat energy by the actual movement of the particles of the medium. So, in the convection, heat energy is transferred. Heat energy is transferred Heat energy is transferred with actual movement of particles of the medium. Actual movement of particles of the medium is what we considered as the convection method. The third method to transfer the heat energy is called as the radiation. So radiation is the third method to transfer the heat energy from one region to another region. But here we don't require any necessary of intertwining medium. So we are going to transfer the heat energy. Heat energy is transferred. Heat energy is transferred without the necessity of any intertwining medium. Without the necessity of any intertwining medium, if you transfer the heat energy, that process is what we call as the radiation. So in the radiation, we are going to transfer the heat energy without the necessity of the intertwining medium. What are the properties of the radiation? Please remember, students, in the case of the properties of the radiation, please remember they travel along straight line, travels along straight line with the speed of light. Radiation travels along straight line with the speed of light. With speed of light. And please remember, they can travel in vacuum. Travel in vacuum. It can undergo the phenomenon of reflection. It can also undergo the refraction concept. And this is going to obey the concept of inverse square law. It obeys what? Inverse square law. Radiation is going to obey the concept of inverse square law. So these are the few properties of radiation. Maybe they may ask to write any 2 or 3 properties of radiation for 2 mark or 3 mark. Now, whenever the radiation is incident on a body, if that body is absolutely or completely absorbs the radiation, then such a body, usually we call it as a black body. So what is a black body? Black body is the one which is going to emit or it is going to absorb the complete radiation which is falling on it. So black body is the one which absorbs all the radiation, which absorbs all the radiation falling on it. If it completely absorbs the radiation, then such a body we call it as the black body radiation. And please remember, student, whatever the amount of energy is absorbed by the black body, that is always directly proportional to the 4th power of its absolute temperature. This is what we called as the Stephen's law. So what is the Stephen's law? Amount of energy emitted per second per unit area is directly proportional to the 4th power of its temperature. To remove that proportionality constant, we are introducing a constant like sigma into T power 4. This sigma is a constant called the Stephen's constant. What is that sigma called? Sigma is a constant called the Stephen's constant. Now, addition with this Stephen's law, you must know the another important law may be asked for 1 mark. That is what we called as the Wien's displacement law. Wien's displacement law. What's the statement of the Wien's displacement law? According to the Wien's displacement law, please remember you can find what is the wavelength corresponding to the maximum intensity of the emission of the black body radiation. Wavelength corresponding to the maximum intensity of the emission of black body radiation is inversely proportional to the temperature. Wien's displacement law tells wavelength corresponding. What is this lambda m? It is wavelength. Wavelength corresponding to the maximum intensity of emission of black body is inversely proportional to the temperature. To remove that proportionality constant, we can introduce the constant that is lambda m into T is equal to a B. That B is a constant called the Wien's displacement constant. What is that B called? B is a constant called the Wien's displacement constant. Wien's displacement constant. So these are the two laws you have to remember, student. That is the Stephen's law and the Wien's displacement law. Yes. Take the next very important concept, student. That is the Newton's law of cooling, which is usually going to be asked for 5 mark. Newton's law of cooling. This is the last concept of the chapter, which is very important, student, for 5 mark. State and explain the concept of the Newton's law of cooling. Now, what is the statement of the Newton's law of cooling? Suppose if I consider one hot body here, let us say there is one body here. Now, let us say the body temperature is T1, surrounding temperature is T1. Then what happens? If I assume T2 is more than T1, if I assume T2 is more than T1, then the amount of heat energy is going to be lost by the body. According to the Newton's law of cooling, Yeah, sorry students, maybe there is some interrupted with the internet. Yeah, sorry students, once again there is some problem in the internet issue. Yeah, we are talking about the concept of the Newton's law of cooling. In the case of the Newton's law of cooling, we have considered a body. Let us write the heading, Newton's law of cooling.
Hello, sir. Evelyn?
Yes, sir.
Yes, ma. Is the class over, ma, or is because I had to leave out of the meeting?
Sir, there's this one concept left, sir, Newton's law of cooling.
Okay. But sir is unable to connect, is it?
Yes, sir, he has some network issues.
Okay. I mean, was it happening in between also, or it is the first time?
No, sir, I guess it happened just now, sir.
Just now, is it? Okay. Sure, Evelyn. So one topic is he was on the way and then he couldn't complete, is it, as of now?
Yes, sir.
Okay, just give me a minute, ma. I will just, if possible, call up. So I think he has left the meeting. Can I call him up and find out if he can continue right now, or he would like to connect it with the next class? Sorry for the inconvenience, students. Just give me a minute. I will just connect with sir and then get back to you. Okay. Dear students, another, I think, 5 minutes of class is there. So just some network issue was there. So sir is joining back right away. Good evening, sir.
Good evening, sir.
Yes, sir. I am just making you the host, sir. Hi, sir. You are the host now, sir. You can present.
Thank you, sir. Fine, students. So we're talking about the concept of the Newton's law of cooling. In the case of the Newton's law of cooling, whatever the amount of heat energy is lost from the hot body to the surrounding, that amount of heat energy lost is directly proportional to the temperature difference. Suppose if I consider this is the hot body of temperature T2, it is placed in the surrounding temperature T1. Then
Jerome, is sir's voice coming?
No, sir.
Okay. I think he has got some serious network issue. No problem, guys. I think we will end the class here right now. I think it is 3:30 now. So there will be a set of physics classes, online sessions this week, as I have informed you last time itself. So this week we will not be having any offline class, but we will be having about 3 to 4 physics classes this week. I will be sending you the schedule by end of today. Okay, students? So you can follow that. And we'll be connecting again in the next week. After Diwali, we'll be connecting offline. But till that point, we'll be having online sessions and majority of the classes will be physics. I'll be sending you the schedule shortly today. Okay, students? Okay, ma, all the
Yes,
best. Take care, guys. See you all. Bye.
Bye, sir.
Thank you, sir.
Thank you,
Bye.
sir.
See you, ma.
Thank you, sir.
Bye.